In this video, we solve problem 8.1.501.xp from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to evaluate the indefinite integral, and we're told to use C, capital C, for the constant of integration. And so we've got this right here. Now, the first thing you want to ask yourself with any integral is, do I have a basic rule for that? And we really don't have a basic rule for this. Let's look at our basic rules quickly. Notice you've got a product. I've got t squared times the cube root of this function here. And we really don't have any products on this list. We've got constant multiple, we've got the sum of two functions, the antiderivative of a constant, power rule, the 1 over x rule, and all of that. There are no products here. Now sometimes we've got products over here on the trig side where you've got secant of x times tangent of x, but for the most part, we don't have a product rule. We don't have a product rule for anti-differentiation. So we've got to do something else. So our basic rules don't apply, we rule that out. Now if basic rules don't apply, the next thing we always try is u-substitution. Now remember, whenever you're using u-substitution, you're looking for a function nested inside of another function. So you want an outside function and an inside function. You're looking for composite functions, and whatever's inside, that's going to be our u. So when I'm looking at this, I'm looking for parentheses, radicals. Sometimes if there's not a lot going on, if it's just a fraction, u is often the denominator. Maybe if it's an exponential, it might be in the exponent. If it's a trig function, it might be the argument of the trig function. You're just looking for a function inside something else. This right here is inside of the cube root function. That tells me u-substitution might be a good choice for this problem. If I let u be this inside function, I'll have the cube root of u right here. Now we're never 100% sure that u-substitution is going to work until we compute du. So we look at the problem, we say, do our basic rules work? No. And then we say, does u-substitution work? We say, well, maybe. I've got a function nested inside another function. So let's just try it. We'll let u equal that inside function, which is t cubed minus 27. Now we'll know that u-substitution will work if we compute du, and a multiple of du is up here somewhere as a factor in our integrand. Now remember how we compute du. Du is just the derivative of this function times dt, the differential of the independent variable. So we'll look at this. The derivative of t cubed is 3t squared. Remember, you bring the power down and multiply by your variable to the one less power. The derivative of a constant is 0, so that's gone. So du is 3t squared dt. And then I'm looking for this up here somewhere. Now, we don't really care too much about the constant because we can always adjust the constants. What we're really looking for is a t squared dt. If there's a t squared dt up here, then u-substitution is likely to work. And we see it. We've got a t squared dt right there. So since we have exactly a t squared dt, I'm going to take this equation and I'm going to solve it for t squared dt. Right now it's multiplied by 3. To undo multiplication, we divide. Or equivalently, you can multiply by 1/3, same thing. And we find out that t squared dt happens to be 1/3 of du. So we choose u first. We compute du. And then we compare du to our integrand. Remember, the goal is to write everything up here entirely in terms of u so that our basic rules will apply. And it looks like I'll be able to write this t squared dt in terms of u because t squared dt is 1/3 du. And I'll be able to write this piece in terms of u because that is the cube root of u. So u-substitution is going to work. We can see that because the t squared dt is there, this is going to work out just fine. So we chose u, we computed du, now we solved for t squared dt. And now we want to write the integral entirely in terms of u. Now I like to rewrite my integrals for this step, especially for students that are new to u-substitution. If you are already comfortable substituting, you don't have to do this, but I'm just going to rearrange it a little bit. I'm going to factor out that t squared, and I'm going to put it over to the right with that dt. And then I'm going to think of this as my u. So this piece right here is the cube root of u. We're literally just substituting. We're replacing this with this. And then this piece, the t squared dt, it can be substituted as well, because that's the same as 1/3 du. So we take that, we rewrote it to make it really obvious what that integral is in terms of u. And then we rewrite everything right here. Now I could write that as a cube root of u. I'm going to write it a little bit differently. Remember this rule from algebra? If you're taking the nth root of x to the m, that's x to the m over n. That index of the radical that goes in the denominator. Now here, I can use that. I can use this rule right here to rewrite this so that that's u to some power if I recognize what my m and my n are. So I say, well, that's u to the first. There's an implied 1 there. And that's a cube root. So this is u to the 1/3. And now I can just use the power rule to take the antiderivative. So you write the integral entirely in terms of u, and the whole point of that is to get here to a point where you have a basic rule for that. So you look at it, you do your u-sub, and you say, do I have a rule for that? And you say, yes, I do. That's just the power rule. So we're going to anti-differentiate using our basic rules. So we bring our constant down, then we add 1 to the exponent. 1/3 plus 1 is 1/3 plus 3/3. So we get 4/3. And then we divide by the new exponent. Dividing by a fraction is the same as multiplying by the reciprocal. So instead of dividing by 4/3, I'm going to multiply by 3/4. And then don't forget your constant of integration. Now the 3's reduce. So that's our answer. That simplifies out front to a 1/4. Problem is, we're not quite there yet. If I take the derivative of this right now, I'm going to get a function of u. And what I'd really like is this function of t that I started with. So we have to back substitute. So after you anti-differentiate, back substitute, which is just another way of saying replace u with whatever it was originally. So we're going to replace u with t cubed minus 27. And that's our answer. I'm not going to check this here, but you could check this. If you take the derivative of this using the chain rule and you simplify, I guarantee you, after using the chain rule and simplifying, you're going to get this as your answer. And that's what it means to compute an antiderivative. The derivative of this is this function that we started with. And you can check that using the chain rule.